In this module on sequential decision analytics, I'm going to return to the universal modeling framework at a higher level of detail than we covered before. Now, I want to mention that my large book, Reinforcement Learning and Stochastic Optimization, has a 50-page chapter on the material that I'm going to be describing here. I'm also at work on a new monograph. It's 200 pages just on the universal modeling framework. That will be coming out in a few months from this recording. So again, modeling these rich problems is an extremely interesting and then complex topic. So think of this as just another step up. There's a lot more to go. So I'm going to start off by talking about textbook modeling styles, just so you have an idea of the range of ways that other books use to model sequential decision problems. So Putterman's book on Markov decision processes, which is the standard reference for reinforcement learning as done within computer science, uses this screenshot on the left. We have time steps, we have states, we have actions, we have rewards that depend on a state action, and we have transition probabilities, which is the probability you land in state S prime given that you're in state S and take action A. And that is the standard canonical framework done in Markov decision processes. By the way, no mention of the objective function. You can see evidence of this in Sutton and Bartow's book. Now, when they write out the objective function, they write it out as the sum of rewards. They optimize over policies. So here's a place where they are optimizing over policies, which I do as well. That's unfortunately not standard, but this is something that they do here. In Putterman, he will optimize over policies and then go running immediately to policies based on Bellman's equation. Now, down here, this is Bellman's equation, where the Q factor, which is a form of value function, is the expected reward plus the downstream value of being in a state. That's Bellman's equation. Britsikas, one of the great names in stochastic control, stochastic optimization, and dynamic programming, he also will optimize over policies. And down here, he's using Bellman's equation. Pretty much every time you see these classic books optimizing over policies, they equate it with Bellman's equation. So they're not really optimizing over policies. They say they want it, the best possible policy, and then they go running to say, oh, but here's the optimal policy. It's given by Bellman's equation. Now, Princeton's reinforcement learning course, they write out the objective function too. Notice that they're not maximizing or minimizing over anything. There's no optimization over policies. They don't ever state what is this an optimization problem over. So this is from their book. They say, what is this optimizing over? We introduce the policy A given S, which is a probability that we choose action A when we're in state S. Now, for some reason, the RL crowd tends to just assume that policies are always random. You won't find that in Putterman's book. In fact, in Putterman's book, you'll find a proof that deterministic policies are better than stochastic policies. How is it that Putterman can prove deterministic policy is better than stochastic policy? Well, it's very, very subtle, but he's solving a different problem. In reinforcement learning, they have a problem that involves learning the value functions, and it turns out in the context of a learning process, randomizing the decision does make sense, but I will tell you, with decades of experience of solving these approximate problems, I virtually never use a randomized policy. So even when you're doing a learning problem where you have to learn the policy, even learning a value function, I will end up using methods that never depend on randomization, and I will make the point of why that is later. Now, the objective function in the Princeton course never answers the question of what it's being optimized over. Instead, the instructor veers into the discussion on the use of randomized policy. So the answer to this question is we are optimizing over policies, and I'll make this point very clear in this module. What's not well understood by the broader literature is what do you mean by optimizing over policies? And soon I'm going to say, well, there's actually these 4 classes of policies, and that's what we're optimizing over. Now, my modeling framework starts off with, we have a state at time t, we have a decision determined by the state and the policy, we have exogenous information that comes in from outside the system. WT is typically also a vector because there's different types of information processes. So a transition function says if you're in state S and you take action X, I use X because X might be a vector, and then you observe the WT plus 1. This is the updated state. That's the transition function, very easy to compute. And finally, my objective function is optimizing over policies. And so I will actually be searching over all 4 classes of policies. By the time you finish this entire module, you'll see a very thorough presentation of all 4 classes of policies. Very brief comment on modeling time. So I used to work in energy. Energy is a fabulous area with respect to timescales. When you go in and work on energy, you're going to have time scales from fractions of a second to seconds. There's certain decisions that have to be made every 2 seconds. There's decisions that are made every 5 minutes. Battery arbitrage decisions made on the scale of hours. There's energy shifting also made on the scale of hours, sometimes days. Demand peak management, peak capacity management, backup power. And the time scales go from fraction of a second to months or even years. Now, in operational problems in businesses and other areas, maybe we don't have quite the spectrum, but we have to be aware that when you have multiple types of decisions, you will often have multiple timescales. For the remainder of this course, I'm going to go from t to t plus 1 to t plus 2 to t plus 3, just to keep things simple. But you have to remember that depending on both the decisions and the sources of exogenous information, you may need to work with different timescales. Now, here's another graph that it's just incredibly important. I had a very difficult time in my career when I didn't understand this, and my former colleague, Erhan Schindler, mapped it out for me, and it was just life-changing. You have to model time using this diagram when you have an exogenous information process. As my colleague, Professor Schindler, put it, t equal to 0 is special. That's here and now. That's what you know now. The first time interval has to be time interval 1. So there's 2 bodies of thought. One is to model the first time interval as 0, and the other is to model the first time interval as 1. What works is to model the first time interval at 1. If you model the first time interval as 0, you will get yourself into all kinds of problems. By starting off where here and now is time 0, the first time interval is time 1, it just puts everything in place. And what it means is that any variable indexed by t is known at time t. And this is incredibly important for modeling. Here's Dmitry Burtsika's very standard notation in control theory. Control theorists write the transition function using f. Their state variable is x, and w is their random variable. Now, he likes to use k for his time index, which is actually fairly standard in controls. But notice how his transition function is computed when you're in state xk at time k, you make decision or control uk at time k, and then you observe information wk. Wk is random at time k. So at time k, x is known. You determine u as a function of x, so that's known given your policy for making decisions, but wk is a random variable. My notation, I use state st at time t. You make a decision based on the state, and the new information is indexed by wt plus 1. I use capital W to emphasize that that's a random variable. Probabilists like that sort of thing. I use this notation consistently. It means anytime you open up any one of my books and you see a variable indexed by time t, you can say it's known at time t. Now, this transition function is being computed at time t plus 1. I'm at time t plus 1, computing the state at time t plus 1, which means st is known, xt is known, and wt plus 1 is known at time t plus 1. It really simplifies all the handling of exogenous information. State variables. Okay, state variables is a big topic. So as I've mentioned, the controls community likes to use X for the information state. Okay, and that's fine. Problem is, there's the massive community of math programming. Anytime you do anything with optimization, you're going to run into the math programming community, and they use X uniformly. So they really own it. The operates research communities, Markov decision process, computer scientists, we all use S. I break the state into three flavors. One is the physical or resource state, RT. There's a lot of people who confuse state and physical state. There's other information about parameters and values and functions. I put in IT. Think of it as anything known perfectly that's not a physical state. And finally, we have a belief state, BT. This is whether you have frequentist or Bayesian beliefs. These are the statistics you know at time t. Now, state variables are a huge topic, an incredibly important topic, and one that's very poorly understood in the sequential decision literature. I'm going to stop here on state variables because I'm going to dedicate an entire module to state variables. So we're going to defer the rest of that conversation just because it's so important and it's such a big topic. Okay, number 2, decision variables. Once again, in operator research, X is a decision. Anytime you see X, it's a decision. Markov decision processes like to use action A. That was introduced by Bellman. In a control theory, they like to use U. I use X. By the way, in the MDP community, A is almost always a discrete action. And in control theory, U is typically a low-dimensional continuous vector, like the forces you put on a robot. X, the style of X is it can be anything. It can be binary or discrete or continuous. It could be scalar or vector. Now, you're going to have a set of constraints that depend on the state. Now, at this point, when I introduce decisions, I do not say how I'm going to make a decision, but I will introduce the function called the policy. And my notation is if your decision variable is little x, the policy is capital X. I use a superscript pi, where pi is not just some arbitrary symbol. It actually contains information. It contains the type of function, little f, and any tunable parameters, theta. Now, I put f and theta in the policy because you have to specify f and you have to specify theta that depends on f. So that when we search over policies, it's clear that we're searching over f and we're searching over theta. Types of decisions, as I said, binary, discrete, continuous scalar, continuous vector, discrete vector, arbitrary. X can be anything. We don't have this culture of action A where some people say, well, I make A continuous or a vector. No, 99.9% of books on dynamic programming, Markov decision processes, and reinforcement learning, it will be action A and A will be discrete. Whereas if you go to the math program community and put down an X, it's well accepted that X can be anything. But also, if you go to packages that need to optimize, you're going to be using a package from the math programming community. Sorry, they own X. Exogenous information. So I use the notation WT plus 1, capital W. I say T plus 1 because I've been talking about the state at time t and the decision at time t. Exogenous information is the information that comes after you make the decision, so I call it WT plus 1. Now, it's perfectly fine to use a generic canonical notation like W, but when you're actually modeling a real problem, you often like to go to actual variables that have some mnemonic value. And so I say, fine. Now, my probabilist friends like to say, oh, they have to be capital letters. And I'm like, nonsense. Sorry, I'm just not going to live with some notation that says anything random has to be capital. First of all, if I'm at time t plus 1, none of these are random. These are all known at time t plus 1. I put hats. If you have an exogenous, a variable that is determined exogenously, put a hat on it. And otherwise, I don't care what variable you use. So R hat, t plus 1, capital R hat can be equipment failures, capital D hat, new customer demands, but little p hat could be a change in prices, that sort of thing. Now, I've also been leaning in the direction of, for my canonical notation, recognizing that W, first of all, is a vector. There's often different forms of information, and typically it's a function that depends possibly on the state and or possibly on the decision. If I have a price at time t plus 1, it may depend on the price at time t, so that's a state-dependent process. If I'm selling stock, if I sell a large number of stock, it'll depress the upcoming price. That's a exogenous information dependent on X. I can be treating a patient Obviously, how the patient responds depends on not only the state of the patient, but also what treatment I prescribe. So this is very general notation. Once again, I always emphasize anything indexed by t is known at time t. So when you say, is that a random variable? I say, what time is it? Now, when we're starting to identify the different types of exogenous information, I've come up with 12 classes of uncertainty from the perspective of a model. If you read down my 12 classes, it has nothing to do with any application domain. Then your challenge is to use this list and say, okay, what are the sources of uncertainty for my problem? So for example, you may make up a list of the 12 classes and say, okay, I'm working in public health. And I can go down each one of the classes and say, okay, what are examples of uncertainty? And when I say uncertainty, what I really mean is exogenous information that fall in that category. Chapter 10 of my big book, Reinforcement Learning and Stochastic Optimization, has an extensive set of examples on this. Now, when you're generating samples of this information, one is to say, let's just use what comes from history. People in finance do this all the time. They're always using history. Now, I can also do what's called a learning while doing, which says, okay, I don't actually have a history. I'm going to actually put this in the field and observe data as it comes in. Now, it's kind of slow. It takes a day to observe a day, but I don't actually have to, in these first two bullets, I don't need to model that process. But then there are times when I do have to model it. And a word for the wise, modeling exogenous information processes can easily be the most sophisticated part of your model because of correlations. Stochastic processes can be very sophisticated and very subtle. So you have to realize that generating samples from a mathematical model, while it can be simple, you can go to a spreadsheet and generate a bunch of random variables, but when you have real-world problems, you want to be able to replicate the behaviors and just get ready that those can be fairly sophisticated. Okay, now we're down to transition functions. Again, the controls community will use little f. They'll take state x. If you're in state x and you make control u, and then you observe wt, which is random, you get the updated state. By the way, I emphasize this notation because this is incredibly useful notation. I have completely adopted the use of a transition function as opposed to a transition matrix. Transition functions go back, well, certainly to the 1950s when transition functions go back to the 1800s. Stochastic control with the W variable, I believe, goes back to the 1950s. These are stochastic problems. I like transition functions. I don't like the notation. So, of course, you've already seen that I use state S, decision X, and information WT plus 1. So the function itself, the letter F, the alphabet is a very valuable piece of real estate. And when you use a letter for something standard, F is a very popular piece of real estate. So when I'm doing the state transition function, I didn't want to use up a whole letter, and in fact, a very important letter, simply because people like to use F for many other things when modeling complex problems. So I use S superscript M. That's the notation I've adopted. It stands for State Transition Model. So that capital M is for model, and this evolves. Now, here I have some examples showing that a state transition model typically is not just an equation. Here's an inventory problem. So the first line is the inventory equation where I take my inventory RT, I add a new inventories that I ordered minus the random demand, I get an updated inventory. So this is a equation that has the state S, the decision X, and exogenous information in the form of d hat. Now the next line, prices, does not have X. It just has PT. It also has PT minus 1. So I need both of those pieces of information, plus a random noise term. Now look at the third line. The third line is the demand at time t plus 1, and I don't have an equation. I just observe it. So this is sometimes known as a model-free process. I don't actually have a model of demand. I just observe it, and I don't have any way of describing how it got there. Now, the last two equations are Bayesian updating, which means, yes, this is also part of the transition function. This is where I'm doing my recursive statistics for updating estimates, whether they're frequentist or Bayesian. Now, the transition function, if you go poke around the literature, especially the controls community, they use all kinds of names for this. This system model and the plant equation. By plant, they mean a power plant or a production plant. Some people even call it the transfer function. I think I came up with 8 or 9 different words in the literature for the transition function. I use transition function or sometimes the state transition model. And it basically gets you from the state at time t to the state at time t plus 1. Now, if you have the transition function, this is a series of equations, very easy to compute because it's always for a single value of the state, a single value of x, which may be a vector, and a single realization of wt plus 1. If you want to do a transition matrix, you're going to get some horrendous equation like this with a multidimensional integral over all the possible values of w. This is completely impossible to compute. It turns out it's also unnecessary. So the community, the very large community in reinforcement learning that adopted this notation from the Markov decision process community, I just don't see why it's used. I don't use it anywhere. I don't even use it in modeling. Because it's not useful, it doesn't communicate anything, and you can't compute it. Okay, finally, the objective function. All right, this is a biggie. First of all, objective functions come in all kinds of flavors. There's a whole range of performance metrics, and I'm not going to say these 7 categories are even complete, but I mean, financial metrics, if you go to a company, they'll give you 50 financial metrics. There's in manufacturing companies, they'll have endless ranges of productivity metrics and so on and so forth. This is what modeling is for real-world problems. Now, let's break down how to write it out mathematically. What we're doing here is we're going to have a bunch of random stuff happening to say, here is how well we're doing. We need to average over anything random, starting with the initial state. Now, the initial state might just be one or a set of numbers, but it may be probability distributions. And it often has probability distributions in the initial state. I don't know how the patient is going to respond. I don't know how the market is going to respond. And I may have a distribution of beliefs in my initial state variable. Now, whether or not you have a probability distribution in your initial state variable, you're then going to simulate the W process. And of course, the W process is a realization of random variables. And you're going to have to take an expectation. Now, I will warn you, when we write that letter, that funny E there of expectation, we're never going to compute it. We're always going to, at a minimum, approximate it, possibly with one sample realization. If you're working in an online problem where you're learning by doing in the field, you're always living one sample realization. But if you're in the computer and you have a mathematical model or you have historical samples, you can loop over some number of samples and take an average and call that approximation of your expectation. Now, we write the value of the policy f pi as a function S0. This is not standard notation. It's my notation, and it's what everybody should adopt because everything that you're doing depends on the initial state. Now, the initial state S0 includes all kinds of information. It includes static information that never changes. Functions, for example, I may just fix a demand function or forecasting function, but there can be static parameters that don't change over time. There can be physical parameters like the standard temperature of a human body or the maximum speed of a car or the point at which water freezes. And then there's a lot of dynamic information. These are initial values. The S0 will contain the initial values of dynamic parameters. The initial inventory is the initial price. Or it could be the starting values in a stochastic search algorithm. By the way, sometimes X here is actually an algorithm like a stochastic gradient algorithm, and the S0 is my initial starting point. Now, the way we approximate the value function, that S0 consists of the initial physical state R0. This could be starting values of inventories of people or facilities, how much cash you have on hand. I0 is parameters and possibly functions, travel times, prices, weather, taxes, tariffs. B0 is all your beliefs. It's all your estimates. It's whether it's frequentist estimates or Bayesian estimates. This is your starting beliefs about anything you don't know perfectly. This S0 is called the state of the world. And when you get out into real world problems, things having to do with the economy or businesses or simply knowing the state of a patient, S0 is a big deal. Simply understanding the initial state is a really big deal. Now, we want to find the best policy. That's called xpi. And pi consists of a function f. Now, this can be a simple rule. It can be a linear function. It can be a neural network. It can be a linear integer or nonlinear program. It can be a math programming problem. So usually it's a human choosing that function. Now, with the emergence of large language models, we're starting to have people play with, oh, let's get the large language model to tell us what rule to use. Don't forget that it is a choice, and it is an optimizable choice. Sometimes the choice will be obvious, and sometimes you'll say, well, there's 3 different functions I could use. Which one is best? Usually it's ad hoc because testing a particular class of policy can be quite a bit of work. Now, to the extent that you have tunable parameters, we're almost always using algorithms to search over the tunable parameters. And maybe we're doing something that's gradient-based, and often we're doing something that does not depend on a gradient. Now, when we're evaluating policy, there are problems where we can prove some theorems and say something about the policy. Early results in inventory problems were proven mathematically. But generally, we're either running computer simulations or most of the time we're running in the field. And so the real world is our simulation. Now, optimal policies are largely a myth. So if you go to the field of Markov decision processes, they're constantly talking about optimal policies. Oh, you have to take a deep breath, get a life. Generally, we're not going to have optimal policies. I'm up to 8 different categories of how to evaluate a policy, and these are all quite important. Number 1 is solution quality. Yes, we do care about solution quality, both on average and worst case. Okay, sometimes policies, because of random variables, work better or worse, and how stable the policy is does matter. Computational speed, both average and worst case, matters. Transparencies, what is the dependence of the decision on the data, because the data might not be accurate. Robustness to data errors, if there's data errors, how flexible is the policy? Tuning requirements, flexibility, adaptability to different conditions. When the world changes, can I adapt my policy? Methodological complexity, I may have to program this up myself. If it's too complicated, what happens if it doesn't work? And this is a very big issue in certain classes of policies. Finally, the data requirements. So when you consider all 8 of these, and these 8 are very important, the notion of optimal always applies to number 1. What is the performance on average? And so we just have to be aware. Obviously, number 1 does matter, but all the others do matter as well, usually as constraints. Now, objective functions can come in 2 broad flavors, and this is often overlooked. Cumulative reward means that I'm summing my costs or benefits over time, which is that's my standard way of writing it. Now, this technically is sort of an online learning. I have to see how well I do over time, and then add up the performances over each time period. But there's also a final reward version where I'm running experiments either in an algorithm or in a lab where I have to do a bunch of experiments. I don't actually care how well I do along the way. I only care how well I do at the end. So I have this variable lowercase x because it's an actual decision, superscript pi because it's determined by whatever search algorithm I'm using, which is a policy. I have that comma capital N because I have a budget and I can run so many iterations, but then at some point I have to stop. Now, I'd like to evaluate that solution. I'm not going to evaluate it based on the W's that I've already observed while I was learning it. I'm going to evaluate it on a new set of W's that I'll call W hat. So this is all carefully covered in Chapter 7 of my big book. Now, let me say a word about risk. Risk is, mathematically, it's an incredibly sophisticated literature, mainly dominated by finance. Finance deals with very specific types of risk measures, and almost virtually no one actually defines risk. So here's my definition of risk in plain English. First of all, you have to define the base objective, and the base objective is always how well you perform on average. So this base objective captures how well any performance measure works. It could be cost per unit, the drug success rate, total profits. It's either a total or an average. These are all variations of the same quantity. And this will handle noise and variations and deviations. Sometimes it works, sometimes it doesn't work. Sometimes the profits are higher and lower. They all average out. And then there were events where that base objective just doesn't capture the event. A fire requiring a plant to be shut down, the death of a patient, profits falling outside the expectations set by management. There are events that are not properly captured by the base objective. This is not a quantitative measure. This is a subjective judgment. You talk about the event, you'll have a human saying, oh my God, that would be terrible. We have to avoid that. So these risk events are handled separately. It doesn't replace the base objective, but you have to blend it in either by adding it to the base objective or more often as a constraint. I use a risk metric rho. And now notice that rho is a function of everything. I don't add things. It doesn't have to be additive. It could be worst case. It could be the second worst. It could depend on specific outcomes. This risk metric can be anything, and it's not even just one metric. I could have a whole family of risk metrics. Now, when you incorporate risk metrics, you can add it to the objective function. Usually you think of risk metric as something bad. So if I'm maximizing, I'm going to subtract it. And I have a tunable parameter that I've called eta here. And again, you may have multiple risk metrics, which means you're going to have multiple etas. Or, and this is often more commonly the case, the risk metric will be subject to a constraint. So I want to maximize my objective function subject to constraints that each metric is less than or maybe greater than some max or min. Okay, for more on this, the universal modeling framework, on the website under modeling, I have a fairly thorough web page on the universal modeling framework. My book, Sequential Decision Analytics and Modeling, it's my teach by example style book. All of the application chapters, which is 12 out of the 14, are on different problems illustrating the universal modeling framework. Chapter 9 of reinforcement learning and stochastic optimization, entirely on the universal modeling framework. I will be coming out with a new monograph soon, 200 pages just on the universal modeling framework.